in computing, the systems we design, the processes we make, they have requirements put on them in terms of speed, cost, and code size. You may be familiar with the term a function being bound. So if I've got something like a cosine wave here, you can see that we have an upper limit, some sort of an m maybe, and a lower limit, maybe a negative n, and the entire time that this signal is going, it stays within those bounds. So typically, whenever you talk about a function being bound, you talk about it being bound within a constant. But when we're going to talk about complexity here. And complexity has a different way of a function being bound. If I have, for example, some sort of a measure of the number of units that our process is going to process, then as this time goes on, or as the number increases, the complexity, whether the performance measure, whether it's time or the amount of space it takes in memory or even the cost to develop it, as we get this n increasing, then we've got some sort of a measure that shows, what the requirements are. And what we're going to do is we are going to look at another function that possibly, will represent, okay, our function, our projected measure of performance for this particular device, it lies within a certain range. And that's really what our discussion today is going to be about. Now, let's think about an example. And in fact, this is going to be a really simple non-computing example. Let's say that I have a square room, and this square room measures n feet by n feet, all right? And I want to tile this room with 6-inch by 6-inch tiles. And let's say that it takes 1 minute to lay each one of these tiles. And I want to figure out, depending on this measurement n, how long it's going to take me to tile this particular room. Well, let's tile a bathroom. Let's say that it's 6 feet by 6 feet. In other words, n is equal to 6 feet. How long is it going to take to tile this room? Well, 6-inch by 6-inch tiles, that's half a foot. So what we have, the number of tiles equals, let's see, we have 12. It's going to take 12 tiles horizontally by 12 tiles, 12 tiles in one direction and 12 tiles in the other direction. That's going to give us 144 tiles. Now, in terms of time, it's going to take us 1 minute per tile. So basically, we're looking at 2 hours and 24 minutes. All right? Now, let's talk about a slightly larger room. Maybe that was a bathroom. Let's talk about, I don't know, how about a kitchen? And a kitchen is it's going to be a square kitchen, but this kitchen is going to be 12 by 12. So in this case, n is equal to 12 feet. Well, the number of tiles in this case is equal to 24 by 24. And what's 24 by 24? It is 576 tiles. And this is going to give us a time of 9 hours and 36 minutes. All right. That's significantly more, isn't it? In fact, you think we just doubled n, right? N went from 6 to 12. But what we did in terms of the amount of time it was going to take in materials, we can also talk about materials here. We look at a quadruple. We look at 4 times as much tiles, 4 times as much time, just by doubling n. Well, let's double n again. Let's say we've got n, in this case, is equal to 24 feet. This is maybe a basement that we're doing. And that will give us 48 by 48 is equal to 2,304 tiles. How long is this going to take us? Well, it's going to take us 38 hours and 24 minutes. a significant increase. All we did was just double it, right? But we quadrupled the amount of material required, and we quadrupled the amount of time it took to do it. So what does this have to do with today's discussion of complexity? Well, whenever we're writing our code, we will see that many times our code will rise in complexity, not necessarily linearly, not necessarily by an exponent like 2. It may actually increase far greater and far quicker than we expect it to. Now, how does this apply to computing? Well, in computing, it could range from anywhere from how long does it take to process something, or how much hard drive space or RAM memory does it take in order to handle this process, or the message traffic. Maybe we've got a network, a cluster of machines that have to pass information back and forth. How much message traffic how much does the message traffic increase if we increase the size of our n, right? Well, this brings us to something referred to as big O notation. Now, big O notation, the term comes from the order of the function. So, order of the function. And the idea is we are going to represent the complexity of our algorithm, the selected algorithm, using this big O notation. Make changes to our algorithm, see how it affects the big O notation, and see if we're actually getting a performance improvement. So when we say that something takes, for example, in our room design, that complexity went as n squared, right? Well, in big O notation, that would be O of n squared. So when we're looking at big O notation, we're looking at different expressions to represent the complexity. Now, the simplest one of all is an order of 1, okay? And that basically is a constant. It means no matter how hard, or no matter how high we make n, the amount of time it takes to do our process, to perform our process, or the amount of space or whatever, the complexity never changes. It stays constant regardless of n. Think of a print statement. Regardless of what value is contained in n, to print n is going to take the same amount of time regardless. Then we start looking at some other measures. So there's order log n. Now, this follows the logarithmic curve, and we'll show you in a minute what that looks like. This is actually pretty good. This is a pretty good level of complexity. In other words, if your function increases in complexity at a rate of log n, you're doing really well. You also have order n to the first, or just n. And this is linear, and it's okay. And it basically means every time I increase n, the amount of resources, time, space, whatever, is going to increase at exactly the same rate as n. Okay? This is, like I said, it's fair. Then we're looking at n log n. And whenever I graph this for you, we'll see how this actually is a little bit more rapidly increasing than n. But it's still, well, it's fair. It's not great, but it's fair. Okay. Now we're going to start getting into some of the bad measures, or the bad relations in terms of complexity. We've got n squared. How about n cubed? This is all getting bad. We also have order 2 to the n. We talked in the last lesson about how 2 to the anything, whenever you folded that piece of paper 42 times, you would reach all the way to the moon. Yeah, 2 to the n, we're getting to some really bad measures. We also have n factorial, and, wow, how about n to the n? That would be horrible. So all of these guys are pretty bad measures, and if you have an algorithm that requires this level of resources, it really behooves you in order to see if you can't simplify the process. Let's take a look and see what these look like graphed out. To get a better idea of the relative complexity of these functions, let's go ahead and graph them using a spreadsheet. I'm going to begin with defining a bunch of different values of n. We're going to start at 2 because for the lower numbers like 0 and 1, some of our functions are not defined. But we're going to go ahead, how about, we'll do up to 15. And then I am going to generate a number of functions. So we will put our functions in a list here. So this is f of n expression. And let's see, the first one was a constant, right? And since multiplication by a constant really had no effect on big O notation, we're going to just do 1. And then we're going to use base 2 log of n. And then we're going to do linear n. Then we'll do n log n. And then after that, we'll do, how about n squared? Maybe even throw in an n cubed, and maybe, how about 2 to the n, and then n factorial, and then the last, the most complex one we'll look at is the n raised to the n. And we'll just do expressions for each one of these. Well, the first one, a constant, that's pretty easy. We'll just put 1 through here. Now what we're going to do is we are going to insert, how about log, and we'll do of n base 2, and we will go and notice that 2 to the 1 is equal to 2, so that makes sense. And we come on all the way down to here, and so there's all of our logarithms, and our log base 2 of n, and you can see that they increase relatively slowly. This column is going to be easy. It's just going to be equal to n. And notice that as we are creating these columns, the function level increases. You know, when we get up to 15 here, we see that every one of these columns is getting significantly larger values for the expression. Now we're going to take, this one is going to equal, let's see, n times log n. So n log n. And we'll copy that all the way down here. Notice, once again, it's increasing in complexity. Then we'll do n squared. All right. Still increasing in complexity. We'll do n cubed. Increasing in complexity still. Now we'll do 2 to the n. Now notice that we had a little bit of a drop here. In other words, the top row where n equals 2, for n cubed it was 8. For 2 to the n it was only 4. In fact, the 2 to the n column stays less than n cubed for quite some time. In fact, it's all the way up until we get to n equals 10, when 2 to the n finally outpaces the n cubed. But notice that as we get further down, that outpacing really grows to the point where whenever we just go 5 more to n equals 15, now it's almost 10 times greater. Now let's look at factorial. So we'll do the factorial of n. That one also is lower. It drops down for the initial values, but as we get higher, notice we're coming much higher. We're outpacing much faster. And then the last one, we're just simply going to do n to the n. So n to the n. And that one really outpaced everybody. Now, what we're going to do is we're just going to simply take these guys and we are going to graph them. So let's go ahead and insert a graph to represent the relative values of this. Now, here's our little graph. Now notice that whenever you're looking at the values that are, the result of our different expressions, that n to the n so much outpaces everybody else that you don't even see any changes in the graph for any of the other complexities. So what we're going to do is we are actually going to change it so that this is a logarithmic scale. And by putting it in as a logarithmic scale, you're going to see, you can actually see the separation of these different functions. So a constant, that's this blue line on the bottom, and then just above that you have log n, and then just above that you have n, and then just above that you have n log n, and then you have n squared, and then this is the n cubed, and n cubed actually starts outpacing most everybody, but it doesn't grow nearly as fast as, say, 2 to the n, which at about 0.10, we notice 2 to the n starts outpacing. And if you were to extend this graph even further out, you would see the separation would continue to grow. And then you've got here n factorial and then n to the n. Well, what you're looking for in terms of positive or good growth for your function's complexity is to stay down here at a constant or log n. Whenever things start getting to a linear growth, then we're talking about fair. But then you get to n log n, n squared, and so forth. You start getting some unwanted growth in your function with increasing values of n. Now, in my experience, there are two primary rules when it comes to big O notation. The first rule is that big O ignores constants. All right. What does it mean when big O ignores constants? Whenever we're looking at complexity, so for example, I showed you big O of 1, right? Well, big O of 1, was constant. Well, if I happen to have two lines of code, so I talked about the print statement, right? If I have two print statements, that's really looking at a complexity of O1, big O of 1, right? Which is really, basic math is 2 times O1. Well, in terms of complexity, growth of complexity for that particular function, we are ignoring the 2. The constant drops out. So no matter how many of these constant functions we have, as long as it's constant, it is considered big O of 1. This is true also if you were to do something like O of n squared plus O of n squared equals 2O of n squared. Well, that 2 drops out. And in fact, if you do the calculation or you do figure out the exact complexity growth of a particular function, and you get something like 4n squared, so we have big O of 4n squared, once again, the 4 will drop out. The complexity of that function will be represented with just O of n squared. Now, the other rule of big O notation is that an expression containing multiple terms, and whenever I'm talking about multiple terms, remember we did that list of all the functions and their relative complexity. We started out with the constant and then went to log n and then went to n and then went to n log n and then n squared and so forth. That is the order of complexity, all right? If an expression contains multiple terms, the terms that dominate will be the terms that define the complexity. What do I mean by that? Well, what I mean is that we showed before, if you've got a bunch of things, a bunch of different processes, and they all add up to kind of this complex expression, the terms that represent greater complexity or greater growth of complexity, those actually hide or get rid of the other terms. Let's do a quick example. What if I have O of n squared plus O of n plus O of 1, all right? Now, which is the most complex function here? Which is the big O notation that represents the greatest complexity? Well, it is this O of n squared, right? That will cancel out or remove any effect of the other two. Why? Well, think of it this way. As the function grows and as we get larger and larger values for n, then, for example, n equal to 100. Well, n squared is equal to what? 10,000? 10,000 is much greater than 100 and far greater than 1, so those start to have far less of an effect. Now when you start talking about n's for 1,000, and it becomes a million barely recognizes the fact that 1,000 is being added to it, and it almost not negligible whenever you add 1 to it. So any expression that contains multiple terms like this, the term that represents the greatest complexity will dominate the other terms, and the other terms will fall out. Let's take a look at some simple code here. Let's just say that I've got a function and it's supposed to come up with a return value. And somewhere in this function, I've defined an I and a j, and I've defined this variable called return value. So I've got return value, and we'll just say that it's equal to I times j. All right? Just a little bit of code here. Now, what is our complexity here? Well, there is no n here. So since there is no n, and even if I and j give us different values, this line of code is executed once. And since it's executed once, right now we have the big O notation 1. But what if in fact we're outputting this guy and we do some sort of a system.out.println return value, all right? What is our order of complexity now? Well, this guy right here, O of 1. This guy right here, O of 1. So it looks like 2 O of 1, right? Well, remember, no constants. And since there's no constants, we just have O of 1. Now, what if we change this so I have a for loop? And my indentation is not going to be quite right here. What if I do for int I is equal to 0, I less than n, I plus plus. And it's just for this line immediately after it. So we are actually looking at an O of n here. This guy is still O of 1. So our complexity is represented with O of n plus O of 1. Remember about our idea about dominating the more complex issues dominating the others. This guy drops out, and our representation in big O notation is just O of n. Now, what if we embed these for loops and have for int j equals 0, j less than n, j plus plus? And so right here, these two lines right here are part of this for loop, and I can actually put curly braces if that makes things a little bit clearer. These two lines, this portion of code right here, inside the curly braces is getting executed n times, but within that block of code, you have this return value is equal to or added to I plus j. This guy is getting executed n times for every time that the outside loop is getting executed once. So our big O notation shows O of n squared here. This guy is still O of 1. It is outside the loop. So you've got O of n squared plus O of 1. That guy drops out, and we've got an order of complexity of n squared. So if you can come up with ways in order to simplify your code so that you don't start embedding over and over again these loops, you're going to significantly improve the performance of your application. The key is to be able to represent your algorithm's complexity using big O notation so that you can compare algorithms and select the one that's going to make it so that your application can reach its performance goals.